So I'll be talking today, I guess you can hear, right? Okay. About amplitudes and cross-sections in 4 dimensions. So the idea is at the explorations we've done are next leading order, but through what I'll describe as local factorizations. By local, this always confused me actually. Local really means in momentum space here, okay? And kind of, well, in this crowd, you know. So it'll describe, depending upon which button. Yeah, okay. It'll describe a bunch of published and to some extent unpublished work, which will hopefully someday appear. The idea is to sidestep infrared regularization through local cancellations in momentum space. And there are 3 parts to this little discussion I'll give. I'll start with what I would describe as a variant factorization, not something that contradicts anything, but just a variation of how we normally do it to organize the knowledge that we already have for hadronic cross-sections. I'll go on to talk about, in particular, virtual corrections that next leading order in the viewpoint that we're going to take here for complex electroweak annihilation amplitudes. And by complex, I mean 2 or 3 or even more electroweak final states. So these will be inclusive cross-sections for those final states, and that means when you get to next leading order, you do have recoiling gluons that are part of what we call the hard scattering function. And the last part will be this returning to this idea of locality, cancellation of final state collinear and soft for electroweak inclusive interactions, the thing that we encountered there. And most of the published work has concentrated really on item 2, but 1 and 3 are different for this. It just add to that for this talk. Okay, and now we're going to, can somebody help me move the page? Suppose I go backward. No. Yeah, it's just the little arrow doesn't.
Sorry.
So it works now, or?
Yeah.
Oh, yeah, so, okay. So this is number 2. All right, so there are only like 17 slides, so we have a chance. Okay, so here's the variant factorization. We're going to talk about this for a few minutes here. The familiar factorized cross-section is in terms of parton distributions. Here, say, quark-antiquark annihilation. If in this particular notation, summing over the quarks means summing over the antiquarks. And so where we produce some state that's denoted Q, and it's a function, you know, it's a convolution of momentum fractions, and here we have Q. Now, Q for us is some collection of momenta of observed electroweak bosons. So you might have 2 Higgs particles, W plus, W minus Z, something like that. So it's fairly complicated, and which we assume to be massive for this purpose. So I won't think specifically about massless photons, but the same basic idea will work. And, you know, it's a phase space like this. I mean, it's complicated, but it's absolutely straightforward standard phase space, but we'll characterize it by measured values of the Q squared, the invariant mass of all of the bosons, and also, if we like, we can look at their rapidities here. And so again, these can be a WZ and so forth, collections like this. It's the wish list sorts of final states as described, for example, in this recent publication about a Lezuch study. So here's our variant factorization. Okay, just let me bring your attention back to the standard factorization theorem, PDF's hard scattering function, which I'll denote here by sigma hat. Our variant factorization, I'm going to just describe it, well, last night. It came to me. We might call it the Higgs scheme. So we'll take AB goes to Q, these are hadrons, and it's still a convolution with a short distance function we'll denote by tau hat, as opposed to sigma hat. And then there's a long distance function F, which includes both of the parton distribution momentum fractions. And basically, it just combines the 2 PDFs, but does not yet go to the point where we cancel initial state infrared divergences and factorize the collinear singularities from each other. Okay, so here, what we get is the part of factorization proves that it's the last part is to cancel the infrared divergences to get what we normally call factorization. This is the step before that where they are factorizable from the final state after we cancel final state interactions. So this is rather a technical point, but this F here you would find in particular would be the same if what you did was produce one Higgs particle. Say QQ bar or GG goes to a single Higgs. And this would be the long distance function, not yet factorized into two parton distributions, but one step before that. That's the viewpoint that we're taking. It kind of looks, this picture is supposed to illustrate this. This is our short distance function in the middle. There are jets associated with the incoming particles. It's a cut forward scattering, so the whole cross section is part of the amplitude, part of this particular imaginary part, where each of these cuts, as we sum over them, includes all the observed particles. So this F matches singularities to everything outside the short distance, the middle part. The F can be defined by the inclusive cross-section for QQ bar. In this case, it's just QQ bar, but obviously we also think about GG. But here it's QQ bar goes to a scalar, and we can pick that scalar for the purposes of this factorization to have the same invariant mass as the observed electroweak bosons that we're talking about. The scalar can be either in the singlet or an adjoint case. And this is really the analog of what used to be once was called a DIS scheme for parton distributions, where you go more or less directly from an observed process. Here, this is not something we observe for the most part, although we do see GG goes to the Higgs. But from a technical point of view, this is equivalent to standard factorization, but with some of the steps in standard factorization not carried out. We normalize F at lowest order to the singlet case, so it's just deltas of 1 minus x1, 1 minus x2. And at higher orders, it would be related to the parton distributions, and it could be factorized into parton distributions in the normal way. So we're just going one step back. All right, whoops. Okay, here we go. Now, why are we doing this? Okay. Because it helps us organize the computation of this tau hat, the short distance function, and hence sigma hat. Tau hat is related to sigma hat just by by essentially the short distance functions of Higgs production. So up to 2 loops, at least, we can organize directly in 4 dimensions and at fixed values of the full set of the observed particles. Perturbatively, we use this F to determine tau hat, and assuming Q represents a color singlet final state, in other words, something we could actually observe at the LHC, the relevant terms are the following. If you if you start with your short distance cross sections, you just make what appear here as subtractions. Okay. And what we want to do is to make these subtractions at the integrand level rather than the integral level. So these will be functions of momenta and loop momenta, but we can do it all in 4 dimensions, okay? So that's the relations are in 4 dimensions, both soft and collinear infrared singularities cancel algebraically, locally in momentum space between the terms that are shown here. We'll have to add some extra terms to make this work, but these extra terms we add all integrate to 0. So they're not subtractions in the sense that we normally think of. So all the mass dependence on and the kinematic dependence on the observed observed momenta can be computed numerically, at least in principle. And this, in principle, we've begun to scratch the surface in making this realistic. We can illustrate the method with next leading order corrections and electroweak annihilation. So we'll just look at the virtual parts first, but all of these terms are there for quarks and gluons. And that's what we've done in the work that we've talked about, we've published. So this is item 2, next leading order process dependence in complex electroweak annihilation amplitudes. We've looked at, in detail at 2 loops for processes. QQ bar goes W plus W minus, GG goes to 2 H's, 3 H's, and so forth. So these are important processes, but they're complicated analytically, and it might be nice to be able to compute them numerically. And we would require momentum space integrals that are infrared finite locally, and also UV convergent. I won't talk about how we incorporate that, but it's possible to do systematically. And it was described in these papers. So we work in Feynman gauge to avoid any non-causal singularities. So these are treated in some sense in this thing I've described as the Higgs scheme. And so what you get for the virtual corrections is simply the matrix element, which is in general a function of an infrared cutoff. As an integral, is P1 plus P2 goes to the observed momenta. Here's our cutoff. And it factorizes in general into a contribution to this the Higgs short distance function times a completely ultraviolet dominated piece. So again, this is for a virtual contribution. So all dependence of the final state is in this ratio of the matrix element to this form factor piece here, which comes from Higgs production. And the rest has all of the Q dependence. The only thing this knows about is the total invariant mass. So all true infrared singularities are absorbed into this F, which cancels in the ratio, and now we can just expand this in the same way. The Hart function is both complex as a number and complicated as an object, as an integral, and includes dynamics of intermediate states in momentum space that are neither soft nor collinear, but it nevertheless can go on shell. These so-called threshold, I would say above threshold is a more accurate statement, momentum configurations are amenable to numerical analysis, either on the form momentum contours in principle or by other means, and a lot of those other means have been described and investigated, and I recommend very recent talk by Matilda Cini at Loops and Legs for the implementation at next leading order at the level of just the NF contributions to the amplitude. This is work with Dario Kemenchah. The essential point is that the singlet QCD form factor enjoys the same factorization as the jet subdiagram. So here we have the object we have here. This is the Higgs cross-section. And it's the same F, but with an H, which we already know. And in fact, has been computed up at least to 3 loops. So here we have the H, again, is this ratio. And we just expand in the loops and solve for these H's, the H for the process we're interested in. And we can get it just at 1 loop and a 2 loop again with these differences. And so the idea is the construction for the Hart scattering is surely true for the full functions, but we want the result for the integrands. And so to be able to give H to the computer, what we want to show is that this and this are integrable functions in terms of the integrands. And now I'll just take a moment to show you how this actually happens at next to leading order. At 1 loop, or at order alpha S squared, but it's 1 loop in these virtual corrections, you have diagrams that look like this. Here we have, say, three vectors in the final state. We have diagrams like this and like this, the triangle-like diagram here, the box-like diagram, and then from the other side. When K gets collinear, K, say, is the momentum of the gluon, either to P1 or P2, we understand we can make collinear approximations, and it's too complicated to dwell on. But the main point is that when we get a collinear singularity here, this K, when it probes the Hart scattering function, is a unphysically polarized gluon. And in the collinear limit, then, K is scalar polarized or longitudinally polarized. We can simply apply the Feynman identity, which just says when you put L slash between P plus L and 1 over P, you get the difference of these two. So very commonly expressed in this kind of figure that shows that as this K becomes collinear, becomes scalar polarized, its action on propagators in the hard scattering is the difference of two pieces. And what happens is that when you add those pieces together, you get a lot of cancellations, and in the sum, you get this factorization. And this is an algebraic relation, which is automatic when we add the integrands of the original amplitude. So this is kind of nice. The only k-dependent factor on the right over here equals the one-loop form factor in the Higgs scheme. And so this the fact that this is true locally, that we can calculate the one-loop hard part by this subtraction, is confirmed locally. And the same is true for the soft limit and the collinear P2 limit. The single term, which is the Higgs virtual, one-loop virtual times the lowest order hard part, serves as a local infrared subtraction for the full set. And there are actually 5 diagrams associated with these two, and also when K attaches to P2. So 5 diagrams of the original amplitude. And the same holds for any electroweak final state of heavy bosons with this initial state, like W plus, W minus, W plus, W minus, or more. So could something like this work beyond one loop? Okay, we've demonstrated locality already very simply and algebraically. And yes, there are some, to get the local relation to 2 loops, it's sometimes necessary, sometimes meaning in some diagrams, to modify the integrand by adding some infrared counterterms. I'll show you what they look like. But actually, it's interesting that when both gluons, suppose now we go to next leading order, and both gluons become collinear to both either on one side or the other side, or one on each side, or one becomes soft and one becomes collinear, you get complete factorization here in the double collinear to P1 limit. This is algebraic and completely local. Okay. So what's really one way of thinking about it is through the Ward, Taylor-Slavnov identities, the hard scattering, in essence, expels the unphysical polarizations, which are what really make subtractions a complicated process. They're simply expelled at the local level if you add up all the diagrams in the hard scattering first. So you don't have to calculate or identify the poles independently. So things get a little more complicated when we try to see single collinear limits, where we have a loop either within an incoming jet or in the short distance function. And here there are 2 things that can happen, 2 qualitative complications associated with the extra loop, which is either in the jet or the hard part. There are terms we call loop polarizations, where the vector here, the polarization of this momentum k, becomes proportional to the momentum flowing in this loop in the jet. So there's like some L mu that has nothing to do with the direction of k. Those all integrate to 0 because the jet one-loop function can't depend on the loop momentum after you've integrated over the loop momentum. But locally, you have to deal with it. And then there's, at the level of the hard part, where you have a loop in the hard part, we have shift mismatches. When H is an extra loop, we call them shift mismatches. The Ward identity requires a shift in loop momentum sometimes when you have a loop of charged particles. And so you have to do something about that. So again, these complications are addressed by counterterms that integrate to 0, but reorganize the integrand. And these are the basic examples. Here, let me flash them. For the collinear singular loop polarizations, we just look at an integrand that has an L mu in it, and then we replace it by yet another integrand. And when we do this, we simply find the loop polarizations are eliminated. This is just by symmetric integration to show that. The shift polarizations are just adding standard diagrams. In this case, in a particular case of for the form factor, you just have these ladder diagrams, and you add to them the exotic color factors. And the only difference between the 2 diagrams is the outer loop is rooted differently in the inner loop. In the 2 terms you take the difference of, so they manifestly integrate to 0. Okay, so the summary for this, that there are more counterterms that I haven't shown, but the ones we've seen illustrate the method. There are not many more counterterms, actually. And with a limited number, we can derive a hard function, H2, that really is free of infrared divergences to next leading order, and we computed numerically. And as I said, this process we're making progress in that direction. So applications with color in the final state remain to be investigated in detail, but really we should be able to do recoiling jets in the final state. And of course, it would be nice to go to higher orders, but these may require further insight. For practical implementation, it's natural to do one integral per loop. This goes by the name loop tree duality across free family, and the one I like is time ordered perturbation theory. And here are some references where people have looked and really made a lot of progress in showing how to do these finite integrals. And so the very last part, this is just a couple of slides, is to take a look at a case where this is a simplified diagram of a single heavy particle and one high PT gluon. So the single heavy observed electroweak is capital Q, the observed gluon is little q. If you look at this in this diagram, you see that when this extra gluon K here becomes soft or it becomes collinear to little q, then you get final state interactions that you would like to see how they cancel and check that they're consistent with this approach. And what the final couple of slides do is they show that indeed that's the case. In this case, we can, in this particular example, we can split things into an initial factor and a final factor. The initial factor is here. You may recognize a kind of denominators from time-ordered perturbation theory. This is actually a sum of two of the time orderings, building on work with Ani Venkata. But the part where we get divergences from is the fact that these two, in the singular limit, these two states A and B become degenerate. And here is what you get in time-ordered perturbation theory. You get the denominator for A times the energy-conserving delta function for B, the denominator for the delta function for A, the denominator for B. You notice the I epsilons are different between the two. And singularities happen whenever omega little q minus k plus omega k goes to omega q. So it's like really simple. And of course, this happens when k equals 0, obviously. And it also happens when k is proportional to q. So the omega just meaning here the energy. And 1 minute, okay, sounds good. After a change of variables, which you can just believe me, as we integrate over the fractional momenta, x's, because this is a cross-section, it's in convolution with our Higgs function or parton distributions, we get a result in which we get a denominator that vanishes, but the numerator also vanishes. So again, you see the situation that if you combine all the terms in what nominally your hard scattering, the cancellations that you look for happen automatically. And the leftover singularities are all in these collinear initial state gluons that are expelled automatically from the hard part, a kind of Meissner effect of perturbative QCD. Work has been done by others along these lines in this spirit. So the summary and for the future, so it is this general Higgs scheme factorization for multi-electroweak boson cross-sections. That's what I've described. There's confirmed locality up to next leading order for virtual corrections. I've shown you how you can imagine doing a cancellation of induced final state infrared divergences without upsetting this locality of cancellations. And pending for the future is the full expressions for cross-sections in addition to the virtual. Complete next leading order numerical integrations is still for the future, and extensions beyond next leading order, which is perhaps a big order, but one can always be optimistic. So thank you.
So, any talks for George? Questions, I mean. Yes, Giulio.
Hello, thank you very much for this great talk. I have a question about these extra putative counter terms that you may need, but they actually integrate to zero. Can you understand the fact that they integrate to zero as a consequence of them being scaleless, or it's completely different?
No, it's kind of focusing slightly differently. The way to think about it is if you take, in QED, if you have a fermion loop, and then you have an unphysically polarized gluon, photon, that you attach everywhere. And you get, through this Feynman identity, cancellation term by term. But at one point, the point is depending upon how you route the momenta, you're going to get cancellation between two terms, one of which the momentum of the photon flows in at the vertex and out through the particle that's already there, and the other one where the momentum of the photon flows into that vertex around the loop and then back. Okay, and so there's a shift, and if the photon is small, is soft, that shift is trivial. But if the photon is collinear, then it's actually a substantial shift of a momentum carried by an unphysical photon. So that's what we call shift loop momenta. And the other, to some extent, are also shift loop momenta, but they rely typically on symmetric integration. Because as I say, the loop momenta have to go away after you do the integral. So can we then re-express the integrand in such a way that these unwanted terms never appear? And certainly in one loop we can do that.
Thanks.
Any more questions?